now.
Hello, everybody. I'm happy to see you today on our Young Seminar Series. This is the part of the big seminar series. And today we have 3 speakers from different places. So I hope we will be expressed with a lot of different research. And I think it's time to introduce our first speaker, Marcela Galvis.
Yes, hello everybody. Our first speaker is Marcela Galvis Restrepo, a PhD student from Copenhagen Business School in Denmark, and she's going to talk about interpretability and fairness of generalized linear models using categorical predictors. The floor is yours, Marcela.
Can you hear me well?
Yes.
Thank you. So, hello, and thank you for coming to the seminar, and thank you for the invitation. So, I am here to present my paper that it's in work with Emilio Carrizosa and Dolores Romero Morales, who are my 2 supervisors, on interpretability and fairness of generalized linear models using categorical predictors. So the motivation for this work is the increasing use of machine learning at high stakes domains. For example, for loan approvals, for pre-trial risk assessments, to identify the most vulnerable people for targeting programs, and school dropout, among other things. And the thing with using machine learning is that when you use machine learning, you use historical data to build an algorithm and then make a decision about something like credit scoring or the other examples that I talked about. And the thing is that since we train those algorithms in historical data, that historical data might be biased against certain groups with certain sensitive attributes. And the algorithms that are built on this data that is biased can also amplify that bias. And here on the right-hand side, you can see an example of the COMPAS recidivism dataset. And here we are trying to predict a 2-year recidivism. Recidivism is whether an individual who is getting out of jail is going to reoffend or not. And here we have some characteristics of those individuals. And the thing is that when we build a classifier for this data set, we find that African Americans are twice as likely to be misclassified as reoffenders than whites when we build a logistic regression or other kinds of models. And then, so in this talk, I'm going to show you some methods that we designed to try to trade off between accuracy and unfairness to reduce this problem that we see here. So there's a lot of literature tackling unfairness in machine learning. And here are some approaches that have been explored. The first one includes modifying the values of a sensitive attribute or the class labels in the training data. And these are pre-processing approaches, but the thing with these pre-processing approaches is that they can have unpredictable consequences for accuracy because you're just changing the data without looking at how accurate the model is. Then there are other methods that try to directly modify the classifier to incorporate fairness constraints. And these methods can reduce unfairness, but they are also classifier dependent, so you have to optimize a specific classifier. And then there are some post-processing approaches that change the threshold for the probabilities of being classified as a positive for different groups. And one final approach, which is closer to what we do, is to learn a fair representation of the data and the model parameters jointly. So in this paper, we are going to search for a representation of the data that shows a good trade-off between accuracy and unfairness. So we are going to trade off between accuracy and unfairness using a method that reduces or transforms the variables in our data set. So, but before talking about that, I have to introduce the definitions of unfairness the definition of unfairness that we're going to use. So there are several definitions of unfairness, usually coming from the legal or the law that defines that algorithms cannot use disparate mistreatment, cannot have decisions that have disparate treatment or disparate impact. And these two notions, the first one is that the decision that the individual receives changes with their sensitive attribute information. And in the second one, the decision outcome disproportionately benefits or hurts members of a certain sensitive group. And the definition that we're going to take is the last one, where we are comparing the misclassification rates for groups of people having different values of the sensitive attribute. And the sensitive attribute might be race or sex. So in this paper, we're using this last definition to define unfairness. Yes, there's a question.
No, I think they confused.
Okay. So so before going into our method for unfairness, I need to explain the background on some previous work which we did on interpretability, on clustering of categorical variables. So in previous work, we are fusing categories of categorical predictors. We designed a method to fuse the categories of categorical predictors that uses accuracy to guide the fusion of these categorical predictors. So let me just go quickly through what we do in that paper and how we use the fusion of categorical features in the paper that I'm presenting right now. So it takes a while. Okay. So as you know, the use of categorical predictors is widespread in many applications. And the usual way to treat them in linear models is by representing each category by a dummy, leaving one out for contrast. And the challenge with this representation is that it can be wasteful, because it can add many low signal regressors. It can be difficult to interpret. It is prone to overfitting. And then it can amplify biases in the data that lead to unfair classification. And so what we propose is a methodology to reduce the complexity of generalized linear models in the presence of categorical predictors. And we are going to cluster the categories using a meta-heuristic approach, where we aim to preserve or even improve accuracy while we reduce complexity. So here, what we are going to do, so we have a training sample of individuals, we have an outcome variable, and we have a vector of input predictors. and we're going to use logistic regression for this problem. And then we have categorical variables within the predictors. And what we want to do is to define or to assume that for each categorical variable, the categories are ordered. So here in the table, you see an example of the ordering of a categorical variable. So this is a nominal categorical variable from the German credit dataset. Here we have an order for that categorical variable according to the coefficients that you would get from the logistic regression, where all the categories are as dummies. So what we do is that we are going to order these categories, and we are going to find two clusters for them. And we are going to guide the process of deciding which clusters we are going to take by out of sample accuracy. So here you see that the categories are we use the concept of feasible clustering, meaning that a clustering is feasible if each of the clusters is a collection of consecutive categories. And we are going to design a heuristic approach to choose which of these different representation of the categorical variable we are going to use. So we design a GRASS algorithm, and then we are going to choose a variable to be clustered in one of its feasible clusterings, and then we're going to move to the next variable to be clustered, and we're going to do that with a greedy randomized adaptive search procedure. So that is the basic idea that we have for the categorical variables, and we are going to use a similar idea for finding a good representation in terms of fairness. So for that, for the first paper, here are the results. We see that we get a model that is good in terms of accuracy compared to having all the variables as dummies. And then the cluster variables give us this result. And we get a model that is much less complex, and so that is good because then we get much less coefficients to estimate. And we are going to be using that idea also for fairness. So we are going to enhance the accuracy and unfairness trade-off. And we're going to, what we do is that we design an algorithm that reduces the possible values taken by the features guided by accuracy and unfairness. And for the categorical features, we're going to fuse together categories to have just one dummy per categorical feature. And for the numerical features, we're going to truncate to the right using the percentiles. Then for each variable, categorical or numerical, we are going to choose a representation guided by the trade-off between out of sample accuracy and unfairness. And this has several advantages, but the main one is that we are getting a classifier that is less unfair, and we can keep accuracy in a similar level than if we don't do this. So I see that I'm running kind of out of time, and I'm going to go through the methodology kind of quick. So we have a prediction problem where we have an outcome variable, and we have some predictors, and we have a sensitive feature set that it's associated to each individual, and we're going to assume that this is a binary characteristic, that the individual is part or not of the sensitive group. And we are going to define unfairness as the difference between the false negative rate for the sensitive group or the protected group and the false negative rate for the not protected group. So in the COMPASS data set, we have about 29% of false negative rate for the Black individuals who are not reoffenders and get classified as reoffenders, compared to 14% of white. So, and then what we're going to do is we're going to optimize this function. We have accuracy, and we are going to give a weight to accuracy, and we have unfairness, and we're going to give a weight to unfairness. So in a nutshell, what we do is that we find a set of good representations for each predictor. We are going to run a logistic regression for each of those representations. We calculate accuracy, this trade-off, and we choose randomly one representation from the top one. Then we build a logistic regression with all predictors reduced to their chosen representation, and we repeat the process a number of times since we have this random part. So let me show you results for 3 data sets. We're going to use the German data set, the adult data set, and the COMPASS data set. With some sensitive attributes. In the German is sex. In the adult, we have sex and also race. And in the COMPASS, we have race as the sensitive attribute. And here is how we define the positive and the negative class. So here you see results for the adult data set. The left-hand side shows what the unfairness would be, or the false negative rate for the protected and the not protected group, and what accuracy would be if we don't take into account our procedure. So if we have all the categorical and the numerical variables in their original representation. And then for different values of alpha, which is the trade-off parameter, which gives weight to the accuracy component, we can get different trade-offs of the false negative rate, the difference in the false negative rates, and accuracy. And we see that accuracy stays the same practically, but then unfairness is reduced to 0 in this data set. That's for race as the attribute, as a sensitive attribute, and this is for sex. We see that the same, that we can reduce basically when we have a weight of 0.4 to 0 the unfairness. Similar results for the German, and we even improve accuracy. And for the COMPASS dataset, we also reduce unfairness, and accuracy stays very similar. So here, some conclusions. I have presented an algorithm that finds an alternative representation of the data while controlling the trade-off between accuracy and unfairness. And for the adult and the German data sets, we find an alternative where accuracy stays the same and unfairness can be reduced to 0. For the COMPASS data set, we don't reduce unfairness to 0, but we reduce it. And our method avoids to give the classifier unnecessary information that might be harmful to especially sensitive groups. Yes, and in the future, we would like to incorporate more than one sensitive attribute, or add the difference in the false positive rate also for to determine, to tackle unfairness in the false positive rate. That is all for me.
Okay, thank you very much, Marcela, for your nice presentation. We will move to our next speaker. I recall the audience that we will place the questions to any of the speakers at the end of the session. So our second speaker is Lavinia Amorosi, who is an assistant professor at the University of Rome, Sapienza, in Italy. And she's going to talk us about a mathematical programming approach to sparse canonical correlation analysis. You can start.
Thank you, Cristina. Can you hear me?
Yes, very good.
Thanks for the presentation. Good afternoon, everyone. And thanks to the organizers for inviting me at this very nice seminar series. My name is Lavinia Amorosi, and as Cristina said, I'm assistant professor in operational research at the Department of Statistical Sciences of Sapienza, University of Rome. In this talk, I'm going to present a very preliminary study on a mathematical programming approach to sparse canonical correlation analysis. This is a joint work in progress with Tullia Patellini. She is a statistician colleague now at the Imperial College in London. Here an overview of this presentation. I'll introduce the context in which this work started. Then I'll briefly recall the main concepts related to canonical correlation analysis and sparsity in this context. Then I'll present the mixed integer quadratic optimization model we formulated for modeling this dimensionality reduction statistical technique. And I'll present very preliminary results and I'll move to the conclusion. So it is well known that in the last 30 years, both improvements in hardware and in optimization methods and techniques produce impressive advances in the performances of mixed integer optimization solvers. Moreover, due to the increasing availability of data, and thus the rapid development of artificial intelligence, we are witnessing a growing interest in the interplay between operational research and statistics. And in this context, we can roughly identify two, let's say, main research directions. Machine learning techniques used to improve operational research techniques and solver performances, like in the work, for example, by Bonami or by Andrea Lodi, and Pischetti, and operational research methods used to improve procedures of statistical models, like in many works by Bersimas, Carrizosa, and Blanquero. This work belongs, let's say, to the second class that I mentioned, and in particular, the availability of large quantities of data that we are experiencing in all sectors like marketing, social networks, telecommunications, and others requires for further improving statistical techniques able to summarize such a huge amount of information in order to extract useful knowledge from it. So in this context, we focused on a dimensionality reduction technique for multiple datasets that, to the best of our knowledge, has not yet been studied from an optimization perspective by exploiting the mixed integer optimization advances, that is canonical correlation analysis, and in particular its sparse variant. We need dimensionality reduction when, in general, when data are big. That is, in this context, we want to represent them by means of lower dimensional structures that typically are obtained as linear combinations of the original variables. Like, for example, in principal component analysis, where we change the coordinate system in order to better account for variability. So among the different dimensionality reduction techniques, canonical correlation analysis is a multivariate statistical technique due to Hotelling in 1936, designed to investigate the relationship between two sets of variables. Each variable represents a different attribute, And we can find example of interest in this technique and in its sparse variant. For example, in the case of genomic data, for example, we can have on the same sample gene expressions data and DNA copy number data. And through this technique, we can find genes whose expression are most closely correlated with a given set of regions of DNA copy number change. Or for example, in microbiome data, we can have, in the case of microbiome data, we can have, for example, on the same sample of patients, nutrient intake data and bacterial abundance data. And through, again, this technique, we can identify the set of the bacterial and nutrient set that are most closely correlated. Indeed, this technique, the goal of this technique is to obtain a lower dimensional representation that retains the relationship between the original data. More in details, we assume to have two datasets, X1 and X2, related to the same sample, taken to be independent, identical distributed realizations of two random vectors. And the goal is to find a pair of linear transformations, Y1 and Y2, that are maximally correlated. So under the hypothesis that the two datasets are centered, we can formulate this problem as the problem of maximizing the correlation between the two new variables, Y1 and Y2, that under these constraints that are imposed to ensure identifiability, since solutions maximizing the correlation are scale invariant, can be expressed as you see in this slide. So the two vectors W1 and W2 that are the variables of this problem are called canonical vectors or weights and assess the importance of each column component of respectively X1 and X2 in explaining the association with the other dataset. And thus they are instrumental for the interpretation of the canonical variables Y1 and Y2 and for untailing the relationship between the two original sets of variables. Obviously, this problem can be solved analytically by means of an eigenvector decomposition. However, when the two dimensions, the two sets of variables P1 and P2 become large, the interpretability of the weights as well as the canonical variables becomes harder. In this case, we need to introduce sparsity. As most or probably all of you already know, sparsity is the property guaranteeing that only a reduced number of variables, or parameters in general, play an important role in the statistical model under consideration, thus improving its interpretability. In the context of canonical correlation analysis, sparsity has mainly been tackled via lasso approach, by adding a regularization term based on the L1 norm, like reported here. So we have the same problem as before, with additional constraints, the ones reported here, where Kj is the maximum number of non-zero components that we want to impose in the canonical vectors. Lasso enjoys popularity in the statistical community due to its good predictive properties. However, in general, it still provides only an approximated solution to the original problem of sparsity. Thus, the idea in this context was to reformulate sparse canonical correlation analysis as a mixed integer optimization problem, the one shown within this slide, where we introduced auxiliary binary variable z equal to 1 if component I of the canonical vector J is non-zero, and thus the logic constraints linking this set of variables with the canonical weights W, and the constraints imposing the maximum number of non-zero components in each of the two canonical vectors. C1 and C2 are positive constants, parameters of the model, that actually play a big game role in the model. while K1 and K2 represent the maximum number of non-zero components for the two canonical vectors. So the idea to introduce auxiliary binary variables derive from the SIMAs, who use the same idea to model sparsity in linear regression. Actually, the use of binary variables for modeling sparsity has been can be found also in the work by Carrizosa and Guerrero for modeling principal component analysis. In our case, the resulting model obtained by introducing this set of auxiliary binary variables is a bilinear quadratically constrained model that can be solved by means of the adoption of one of the most recent Gurobi modules able to solve this class of problems. So we tested up to now only on simulated data. As I mentioned, this is a very preliminary study. We generated this data according to the model reported here, that is the one adopted also in work by Daniela Witten, where each component of the error matrix epsilon I follows a normal distribution with zero mean and standard deviation 0.1. Moreover, we consider two different scenarios with respect to the number of variables P1 and P2, that is the two dimensions of the two sets of variables, and a different level of sparsity, as reported in this table. So for both scenarios, we consider, let's say, a lower and a higher level of sparsity by changing the number of the parameters K1 and K2. Moreover, we generated the U vector, the one used in the model for generating the simulated data, from an n variant normal distribution with zero mean vector and identity variance covariance matrix. And we consider three different sample sizes equal respectively to 50, 150, and 500. So here we reported the results obtained running the model on this on the first scenario, in this case, with a lower level of sparsity. On the left, we have the values of the W1 vector, the first canonical vector. On the right, the values for the second canonical vector, W2. The black stars represent the true values that are compared with estimated ones for each component of the two canonical vectors. And the colored dots represent the estimated values corresponding to the different sizes considered in this test. So we can observe that the estimated values become, as expected, closer to the real ones as the sample size increases. This is an expected behavior. Indeed, the empirical correlation, that is the objective function to maximize in the model, is a less reliable measure of the dependence between the random variables we are trying to summarize when the sample size is small. And thus, when the sample size increases, the same measure better captures the association between the random mechanism generating the two original datasets. The same result, the same comparison is reported here for the higher level of sparsity on the same scenario. We have only one non-zero components for each of the two canonical vectors. And we can see that in this case, for all the sample size, the model is able to correctly compute the true values of the canonical weights. And a similar behavior can be observed also on the second scenario, both for a lower and for a higher level of sparsity. So based on these, I repeat, very preliminary results, the main insights we can extract are that the sparsity pattern appears to be well captured in almost all settings among the one we tried. The direction of the association is the sign of the canonical vectors is always correctly identified. The model seems to be able to deal with a sparsity level on more than 90% according with the results of this last scenario with a higher level of sparsity, and as expected, the estimated values become closer to the real ones as the sample size increases. So, in conclusion, in this very preliminary study, we presented a new mixed integer quadratic optimization formulation for sparse canonical correlation analysis. Very preliminary test validated it. Obviously, in the following work, we have to test on more challenging settings the model as well as real data examples, and also investigate the possibility to embed additional properties into the formulation, like for example also the possibility to deal with more than 2 data sets, so more than 2 differently from this first experiments. This is a joint work in progress, as I mentioned before, with Giulia Padellini, PhD in Statistical Sciences. Here I reported the link to the technical report related to this preliminary study. And here some useful references. And thanks for your attention, and thanks again to the organizer and for this very nice opportunity. And I would like to take this opportunity also for congratulating with Cristina Molero de Rio for the Young Women for OR 2021 award. Thanks again.
Thank you very much, Lavinia, and also for your presentation. That was very nice. Now we will move to our last speaker, who is Yujia Chen, PhD student from the University of Edinburgh in UK, and her talk is entitled "Effects of Imbalanced Datasets on Interpretable Machine Learning." The floor is yours, Yujia.
Thank you. So good afternoon, everyone. My name is Yujia Chen, and first I would like to thank the organizers for organizing the seminars and also for inviting me. And so today my research topic is about the effect of imbalanced data size on interpretable machine learning, which is supervised by Dr. Belen Martibergen and Dr. Rafaela Calabrese. So today I will mainly talk about 4 parts. So first, I will briefly introduce the related literature of my research topic, and in the second part, I will briefly show you the experiment process and the main objective of my research, and also I will present some initial results of I have got for now, and finally, I will talk about the potential future research of this project. So first is about interpretable machine learning. So it emphasizes the balance of the predictive accuracy and interpretability. So it's really important when we're using machine learning to make high-stake decisions. So for example, in the credit scoring domain, there are already regulations like GDPR has provided the right to an explanation of credit decision for a customer. But there are many black box machine learning techniques, such as the neural networks, support vector machine, random forest, gradient boosting, are increasingly applied in credit scoring domain because of their superior predictive performance, but their lack of interpretability. So some model agnostic interpretation methods are used at a second stage to explain the prediction results generated by these black box machine learning models. So for example, the Landberg and Lin 2017 introduced SHARP, which calculates the average contribution of a feature value to the predictions. And also Apple in June 2016 introduced accumulated local effects plot, which visualize how the model prediction changes on average if the feature value varies. And also Ribeiro et al. In 2016 introduced the lab, which used the interpretable models such as logistic regression to interpret the individual predictions directly. So today I will focus on the interpretable results generated by Sharp. So besides the requirement of interpretability, another common problem is in the classification field is the class imbalance problem. So it occurs when the number of observations in the minority class is much less than that in the majority class. So it's really common in the credit scoring domain because the number of the bad borrowers is much less than the number of good borrowers, and they are really common in many other application fields such as cancer diagnosis, natural disaster predictions, fraud detection, etc. So the main problem here is that in the classification models, the estimate of the dependent variable tends to be biased towards the majority class. So finally, the minority class, the rare events which we are really care about, are ignored or worse identified by these models. So there are already some researchers have shown that some black box machine learning models such as random forest, gradient boosting, and neural network are more robust to differences in class imbalanced compared to the simple but interpretable models such as decision trees, linear discriminant analysis, and logistic regressions. And there are already many researchers have proposed the imbalanced learning techniques to achieve better classification performance, such as some sampling methods and cost-sensitive techniques, etc. So here we can know that the current research has mainly focused on the effects of the imbalanced datasets on the predictability of these machine learning techniques and how to improve it, while the impact on the interpretability has never been studied before in the literature. So suppose the robustness of the interpretation methods could be disturbed by the class imbalance, people should pay attention to the authenticity of the interpretation results provided by these methods when applying to the imbalanced data sets. So for example, when we're using the black box machine learning models to get the results like the loan needs to be rejected, the customers may ask why is the result. So in the second pictures, when we add a layer of interpretation methods in the second stage, we can get the explanation that the loan is rejected because there are many different reasons. But the problem here is what if we have the imbalanced data sets, which is, as I said before, is really common in the credit scoring domain. Are these explanations still reliable? So if they're not reliable, it can cause financial losses of the banks because they rely on these explanations to make their decisions, and it can also misleading the customers. So here is the main objective is to examine the robustness of the interpretations generated from the imbalanced data size. So here we first choose XGBoost, which is superior in the which has superior predictive performance in the credit scoring domain, and we choose Sharp because it has it's really popular in interpreting black box models in the credit scoring domain also. So the most used interpretation results of Sharp here is the rank list of the features based on their importance, which is measured by the mean absolute Sharp value. So here is an example of the feature ranks in the credit scoring domain. So in the x-axis is the mean absolute Sharp values. In the y-axis is the feature rank. So we can see that the features ranked higher if they have more if they have larger mean absolute Sharp values, and which shows that they are more important. So here the to examine the robustness of the interpretation methods, the idea is to examine the consistency of the sharp feature important rank list generated from the data size with different level of imbalance. So if the rank list generated from the imbalanced data size are still consistent, we can say like it means that the interpretations are robust. So here we first briefly introduce the data and the sampling process I used. So we used the residential mortgage data in the UK between 2016 and 2020 from European Data Warehouse. So we identified the independent variable as loan default quarterly and collect the explanatory variable 1 year ahead. So finally, we got these 3,000 defaulted loans. So as I said before, since we need to examine the consistency of the interpretations based on different level of imbalance. So during the sampling process, we need to generate the data size with different default rates. So we first generate the data size with 50% default rate. So all the defaulted loans are selected, and we randomly selected the same number of non-defaulted loans. So finally, we got the sample size, which is this 6,000 number. And here, because we only want to change the default rates, but not the sample size. So we fix the sample size at the 6,000 number, and we undersampling the defaults, and we also randomly sampling more non-defaults to build data size with smaller default ratios to 1%. So here is the final framework. So after data preparing and sampling, we split each data size to train and test set, and then we train the X3 boost on the training set. Here we use each measure as a performance matrix, so which is a similar matrix as AUC, but it gives greater weights on correctly classifying the default cases than on correctly classifying the non-default cases, so which is preferable for the imbalanced data size as our case. So after getting the model with the best tuned parameters, we employ it on the test set, and we get the H measures. So here we restrict the value between the 0.18 and 0.25, and we repeat the process until we meet this criteria. So the reason why we set this criteria is that we don't want the prediction performance of the models affect the interpretations. So here we did an initial experiments. So we generated 30 data sets for each default rates, and we trained 30 XGBoost models and tested them on the test set, and finally got like 30 H measure values for each default rate. So here is the box plot of the H measure values. So we can see that actually the prediction performance varies a lot, especially among the models building on the imbalanced data size. So here we selected the models between these, like we set a restriction from like 0.18 to 0.25 to get the models which can have the similar but also reasonably good prediction performance. So back to the framework. After we meet these criteria, we compute the sharp feature importance, and finally we got the feature ranking based on their importance. So we repeat all the framework 10 times. Finally, for each default race, we will get like 10 rank lists to examine the robustness of the interpretations of sharp. We can examine the consistency among the 10 rank lists for each default rate. So here we need a method called sequential rank agreement to check the consistency among the rank list, compare the consistency for different default rates. So the sequential rank agreement is calculated based on the set of unique items in list depth for all the lists. So for example, in the left tables, there are 3 lists with like 5 unique items, and in the right tables we can see that in the first list steps they are like a set of items of A and B, and since the set of items are accumulated. So for example, when the list depth equals to 2, it will have like 3 unique items, which is A, B, and C. So we use this method here. So we first calculate the sequential rank agreement for each atoms using the following formulas. So this function has an interpretation as the expected Euclidean distance of the individual ranks from the expected ranking over all the list. So then the financial sequential rank agreement for each list depth over all the list can be calculated as the weighted expected agreement of all the atoms in the list. So here we can know from this formula, we can know that the larger the value of the SRA, the more disagreement in the list. So for example, if all the ranks of all the rank lists are the same, so finally for each atoms we can get a 0 for each. We can get a sequential rank agreement of 0 of each items. So the final sequential rank agreement of all the lists will also be 0. So it means that the rank lists are all the same. So by using this method, we calculate the SRA of the 10 sharp feature importance rank list for each default rate. And here is the final default, this line chart. So we can see that in the x-axis is the default rate, and in the y-axis is the SRA values calculated. And in this line chart, each line represents the same list depth. And here we only show like 4 list depths, and we got like 40 list depths, which is the maximum list depth, because we have like 40 feature values, because we have 40 features, and each point on the line represents the rank agreement value of the 10 sharp feature importance rank list of each default rate. So we can see that the rank agreement values are larger in the data size with smaller default rates, and although it's kind of like fluctuated, it shows a decreased trend, which means that the rank list show more agreement or more consistency in more balanced data size. So here we can get a conclusion that Sharp can achieve like more consistent interpretation results in more balanced data size. So here is the initial results, and finally the future research about this project is that I will like finish the experiments by investigating more issues of interpretations of Sharp, and also some other like interpretation methods like line, more, and some accumulated local effect plots caused by the imbalanced data size. And also I will like identify the effects of the imbalanced data size on the model agnostic interpretation methods on a theoretical level. And finally, I will suggest a method for assessing the interpretability of machine learning model that takes into account the imbalanced data size. So here are some references, and thank you for listening. That's all from me.
Thank you, Yujia, for your great presentation. Sorry for my pronunciation. So I want to open the floor for questions because yeah, we are in time, and we have some time for questions. You just need to, if you have a question to any of our presenters, you can raise your hand, and then we give you an opportunity to unmute yourself. Or of course, you can use chat as well. So probably while our attendant think about the questions, I can ask you, Yujia, about your model. Yeah, is it actually model dependent? Do you need XGBoost for your one of the step, or you can use other black box methods instead of XGBoost as well?
Yeah, I can use, like here I chose attributes because like it shows superior predictive performance in the credit scoring domain, but I can also like choose other many different black box machine learning models like neural network or something like that. So here, like for the experiment I did for now, is I only use one black box models, but in the future I could also use many different models in this experiment. Yeah.
Okay, great. Yeah, thank you. I see your point. Yeah.
Yeah.
So I have actually one more question to Lavinia about yeah, it's a little bit simple question, because I've seen your model, Lavinia, that you are using regularization term as a constraint. What actually the motivation to use it as a constraint, because you can add this to the objective function. Yeah, so my question is, why not to add it to the objective function?
Oh, you mean the constraints in which I impose the maximum number of
Yes, yes.
zero components? Actually, as I mentioned, we derived this idea by studying mainly papers by Bersimas, in which this the sparsity is modeled by introducing this set of auxiliary binary variables and thus used to include additional constraints to the model. The resulting model is a model that can be solved actually by exploiting this recent module by Gurobi. So we didn't consider at the moment a different way to model sparsity, but for sure there can be other way to do it.
Oh,
For
I see.
future.
I was thinking that you have special reason for that. So yeah, okay, I see. You just yeah, it's just because of preliminary results. Okay, I got it. Thank you.
You're welcome.
Is there any other questions in the audience? So it seems to me either everything was clear. Okay, we have one question. So Paula, yeah, Paula, you now have rights to unmute yourself. Yeah.
Hello.
Hello.
Hello. First of all, I'd like to thank the organizers for this great seminar series, also the students sub-series, let's say. And I'd like to congratulate all three speakers. These are really interesting talks and all very clear. So we have to think to have some questions, as you could see. So this was really nice. Thank you very much.
Thank you.
I was having video here. So I have just a short question for Marcela. Maybe I was inattentive at some point. You were introducing this concept of feasible clusterings. I mean, you are grouping the categories, right? You are grouping the categories of the categorical predictors. And you had this concept of feasible clusterings. But so that some groups of categories are acceptable and others are not. And this was, if I followed well, that you only allowed for consecutive categories to be grouped. But this, of course, only applies if the categories are originally ordered. Most of the time they are not.
Let me
just finish. If they are not ordered, then any grouping is feasible. I mean, there's no criteria there. And in that case, doesn't the problem become too combinatorial?
Yes, we reduce our set of feasible clusterings by considering that the coefficients can tell us this order. So if it's an ordinal categorical variable, then it has a natural order, and then we use that order. But if it's a nominal categorical variable that doesn't have an order, a natural order, then we use the coefficients from a logistic regression where we include all the dummies, and then we are going to order according to those coefficients. So in a way, we are saying that categories are similar if they have a similar effect on the response variable.
This you mean, and this criteria you then use to group them?
Yes, yes.
Okay, so that I had not.
Sorry, it was not clear before. I think I went.
Yeah, well,
very
it's
quickly,
many
but,
things
yeah.
at the time. Thank you very much.
Thank you.
Okay, thank you very much for your question, Paula. I don't know if there are no more questions from the audience. I think we can stop our seminar and again say great thank you for all of our speakers.
Thank you very much for the invitation and for the nice talks also. Oh, okay.
Thank you very much, everybody,
Thank you
for the nice presentations. Thank you, Laura.
Thank you. Bye.
Thank you.
Thank you.